So today we are going to review Unit 7, which is exponentials and logarithms. And first thing I want to review is how to graph an exponential. And what I have here, just two little examples so we can practice. Easiest thing I can tell you to do is make a table. So I'm just going to do x, y. And what I would do is base my table off of the exponent. Whatever would set your exponent equal to 0, in this case it would just be 0, I would put that in the middle of the table. And then do two numbers that are bigger, two numbers that are smaller. You can plug these values into the equation by hand, or if you have a graphing calculator, you can use that too. Now, the other thing I want to remind you about is anything that is added or subtracted. I have this plus 1 here. That would take, if we just had y equals 2 to the x, if we took and added 1 to it, this would take that graph and shift it up 1 unit. And that number added there on the outside is also going to be your asymptote. So you have a, I like to call it horizontal line at 1. Equation of that line would be y equals 1. That's your asymptote. And again, you can plug these numbers in by hand, or if you want to do this on the graphing calculator, I'm just going to hit my y equals button to save a little bit of time and type that function in. So 2 to the x plus 1. Once you type it in, just hit second graph, and that should take you to the table. You can move this up and down. And I'm just going to record these values here real quick. So I've got 1.25, 1.5, 2, 3, and 5. And 5 points should give you a really good idea of the graph. And like I said, pick whatever would set that exponent to 0 to put in the middle, and that'll be kind of the middle of the graph. And we're just going to estimate. If these are not nice values, just kind of estimate. So 1.25 would be just a little bit above that. 1.5 kind of in the middle there. 0.2. 1.3 is on a nice point. 2.5 is on a nice point. If I continued that table, maybe got another point there, you guys can see 3 goes with 9. So just to get a little bit better idea of the shape here. So if we're at 3, we're going to be up at 9, and then this is going to be curved. And remember, it doesn't touch the asymptote, doesn't go over, it gets really small. These numbers would get closer and closer and closer to 1, but they would never actually reach 1. And I should have put this on here, but let me write down the domain and the range. So the domain for any exponential function, this goes left forever, this goes right forever. So it'll cover the whole x-axis from negative infinity to infinity. When you do the range is how you move up and down possible y values. You don't touch any part of the graph till you hop over that asymptote. And remember, you don't actually touch the asymptote. So we're going to start this at 1. And I'm going to use a parenthesis instead of a bracket because I don't actually touch the asymptote. And then that points up forever. So that's going to go up to infinity for my range. Okay, so similar graph here. Difference is I have an exponent that's a little different, and it's whatever would set this equal to 0. So it's always the opposite of what it looks like. So this would actually shift your y equals 2 to the x 1 unit to the left. So it would take this graph we just did. It's not going to be on the asymptote. I'd have to shift it back down, but it's going to move it over to the left. Okay, now when you make your table here, this I would do a little bit differently than the previous question. I would put whatever sets that exponent equal to 0 in the middle of the table. So the middle of my table would be negative 1. And then just a couple bigger numbers, I would do 0 and 1. A couple smaller numbers, negative 2, negative 3. And again, if you don't have a graphing calculator, you're going to plug those in for x and your exponent. If you do have a graphing calculator, I have mine laying here, what I'm going to do is just type that equation in. So 2 to the x plus 1. And if you can't see the exponent, you want to put parentheses around it to make sure that the x plus 1, that whole expression, is in the exponent. And then once you got it typed in, second graph to get your table. And at -3, I got 0.25. -2, I've got 0.5. -1, I've got 1. 0, I've got 2. And at 1, I have 4. Because I don't have anything added or subtracted to this, the asymptote is just going to be excuse me, the x-axis, which has the equation y equals 0. That's because nothing is added or subtracted to that 2x plus 1, or 2 to the x plus 1. So when I plot these points, they're going to get really close to the x-axis, but they're never going to touch it, never going to go over it. And again, if it's not a nice number, just do your best to kind of estimate. And I'm just plotting these points here. 1, 4. And if I pull the table back up again, if you guys want to get another point, at 2 I'm at 8, just to kind of get a better idea of the shape here. So this goes up pretty quickly. And looks something like that. Now, the domain for that graph is the same, -infinity to infinity, goes left and right forever. The range here, you start touching the graph after you hop over the asymptote at 0, so it'd be 0 to infinity because it goes up forever. The other graphing we did in this unit was to graph a logarithm, and I'm just going to write a little note for you at the bottom here. If you have the log base b of x, and you can go back to your notes where we graphed this, which would be 7,4 if you want to look at that. You always have the 2 points, what we call our parent function here. I just have the log base b of x, and I can interchange any base I want here. If I were to make a tiny little table just for this graph, anytime you have a log function, just the log of x, nothing else, you have the point 1, 0, and you will have the point b, whatever that base is, 1. So the graph we're going to work with in each of our examples is the log base 4 of x, and each one of these is a little different, but it's a log base 4. So if I have the log base 4 of x, y equals that, what I'm going to call my parent function points would be 1, 0, and 4, 1. We're just going to sketch these graphs. I'm looking for a general shape. And I'm going to come over and remind you, the log is actually the inverse of an exponential. So if you guys want to look at these ones we just did real quick, what it's going to do is it's going to reflect something with a similar shape to that exponential over the line y equals x, and it's going to kind of turn it the other direction. So I'm going to remind you how to do this here. Now, you cannot take the log of a negative number. So the asymptote for a logarithm is actually going to be whatever would start to set that equal to 0. So what would set that equal to 0 is actually 0. The asymptote for a log function is going to be a vertical. I'll call it vertexal, so I remember vertexal line. So here my asymptote would be x equals 0. Now, I'm just going to plot these 2 points. Here's 1, 0, and 4, 1. And I'm just looking for you guys to get the general shape here. They all look similar to this. And that's what I would be looking for. I don't want it to touch that asymptote or go over it. Your log function is going to look like this shape right here. Okay, now we're going to shift in these other 2 examples. So not part of the logarithm, this -3 would take the graph we just sketched here, and this would shift the graph down 3 units. Now, what you want to do if you're shifting down, I'm going to take those original 2 points that I had, the 1, 0, and the 4, 1. If I'm going to shift down 3, all you're going to do is subtract 3 from the y coordinate. If you move up or down, you're going to subtract or add from the y coordinate. If you move left or right, we'll do that in the next question. So this shifted down is going to convert these 2 points to be 1, -3, and 4, -2. I'm sorry. Yes. So we're just going to shift these down. So this point down 3 units, this point down 3 units. The x-coordinate would stay the same because we're not shifting left or right. Now, the asymptote, there's nothing with the x, so the asymptote does not change. We're just going to shift it down. The asymptote is still going to be x equals 0. So when I put this on the graph, 1, -3, and then 4, -2 would be about right here. Same shape as this. We're just going to go and shift it down 3 units. So I'm looking for that for your general shape. Okay, sorry, let me back up. Let's do domain and range. The domain of this first graph, you don't start touching x values till you hop over that asymptote. So again, we're not going to use a bracket, but right after 0, I would have the graph close to that, goes to the right forever. And the range for any log function, and I know this is kind of weird, this goes down forever. This does not flatten up, and it kind of looks that way. It goes gradually up forever. It just goes very slowly. So -infinity to infinity is going to be the range for any of these graphs. This graph actually has exactly the same domain, -infinity. Oops, sorry. Sorry, let me start that over. The domain here is going to be 0 to infinity. The range is going to be -infinity to infinity. And we've got one more here. Now, inside with the x, you can't take the log of a negative number, so I'm trying to find the value that would set that equal to 0. It's always the opposite of what it looks like, so it'd be -2. What I'm going to do here, this is going to shift the graph left 2 units from that original one that we just did at the very beginning of the problem. So I'm going to have those 2 parent function points for the log base 4 of x, and we are going to take and we are going to subtract 2 from the x coordinate. If you move left or right, that's going to affect the x coordinate, so -2, so this is 2 units left is how I would describe that. So the y coordinate is going to stay the same here. That 1, 0 is going to become -1, 0. I'm subtracting 2 from the x coordinate. And that 4, 1 is going to become 2, 1. The y coordinates will stay the same. So -1, 0 would be right here. 2, 1 would be right here. And we're taking that original graph that we did in part A and just shifting it over 2 units to the left. All right. So the next question, does the function represent growth or decay in what percent? For growth or decay, A has to be positive, and you're going to have that in both of the questions I have there. If A is negative, it's neither growth or decay. So I have 0.6. This is my A value. That's positive. Okay. If the B value is greater than 1, then you have growth, which is what we have here. So this is going to be exponential growth. Now, to find the percent that they're talking about, the growth factor is 1 plus the rate. So you have this 1.12, 1 plus your rate. If you go through and solve this, you're going to get 0.12 as your rate. And so that's going to be a 12% increase, or a 12% growth is what's going on there. Just multiplying that by 100. Okay, now both of these, like I said, in number 1 and number 2 have a positive A value. If the B value is between 0 and 1, it's not allowed to be negative, but if it's between 0 and 1, which it is here, you're going to have decay. Now, if you have decay, your decay factor is 1 minus the rate. So for this problem, I have 0.4 equals 1 minus the rate. If you want to go through and solve that, you're trying to figure out what percentage you're taking away from 100%. This would be 40%. So what am I taking away? This is going to be a 60% decay. Whoops, let me spell that right. You could get 0.6 if you solve this little equation. So it's going to be 60% decay. Okay, using AB to the x for number 3. x and y, x and y. What you want to do is set up a system, and you want to start with the point that has the larger x value. So 3 is bigger than -1. What you're going to do is plug those values in for x and y in your general form, y equals ab to the x. So that's what I'm doing here. And what we do with this system is divide the bottom line by the top line. The reason we do that is because every time you have a divided by a, and that's going to cancel out. So what I'm going to do is 192 divided by 0.75, and that's going to give us 256. Okay, now when you divide like bases, I have b to the third divided by b to the -1. If you are dividing like bases, you subtract the exponents. This would be 3 minus a -1 would be one way to do that. Or you can move this back up to the top, and that would become a positive, or b to the +1. Either way, you should get b to the 4th when you divide these two. And then all we have to do is take a 4th root. We do not put a plus and minus symbol here because in an exponential the b value is not allowed to be negative. So we're just doing the 4th root of 256, which is going to give you 4. Alright, once you have that, you have to find the a value, and you can plug this into either equation. I would probably plug it into the one that had the positive exponent just to make it a little bit less work. So 192, I still don't know a, but now I know b is 4. So I'd have 192 equals a times 4 to the third. 4 to the third power is 64. And so I'm just going to divide both sides there by 64. And if I take 192 divided by 64, we're going to get 3. Now, my actual answer to the question, I want it in this format. So my actual answer to the question, y equals 3 times 4 to the x, replacing a with 3 and b with the 4. And we've got several equations here that we want to solve. Just different, round to the nearest thousandth as needed. Here I have log base x of 243 equals 5. If I want to get rid of the log, all I've got to do is swing the base to the other side. So I get 243 is x is going to push that 5 up in the air. And I need to figure out what to the 5th power is 243. Easiest way I can tell you to solve this, we're just going to take both sides to the 1/5 power. And if you do that, you should get x equals 3. If your variable is in your exponent, which it is in my next question, we're going to use a log. First thing I would tell you to do there is get rid of that 4 in front. We're going to divide both sides by 4, trying to get that exponent isolated. So I've got 5 to the x minus 7, 230 divided by 4. This is going to be 57.5. Only way to bring that exponent down on the level with the rest of the question is to convert this to a log. So I'm going to swing this 5 across the equal sign. That brings the exponent down on the level with the rest of the question. And that base of my exponent becomes the base of my log. So log base 5 of 57.5. Okay, now the calculator only does base 10. So I'm going to do the change of base formula on this. It'd be the log of 57.5 divided by the log of 5, which I'm going to grab my calculator for. So log 57.5, make sure you close the parentheses, divided by the log of 5. And then to that answer, I'm going to add the 7 to get it away from the x. And we're going to go 3 decimal places here, so 9.518. And very easy to check this by plugging it back into the original problem. Okay, next one we have some logarithms that are natural logs, the ln. And we got some properties here, so I'm going to condense this into a single natural logarithm. This set of properties works for regular logs too. I got my power property right there, where anything that's multiplied by a log or natural log becomes an exponent. So this would be the natural log of 4 to the third. I can further squish this together. I'm just going to jot this down. 4 to the third is 64, so I'm going to use that in the next step. When you have addition, you're going to squish that together with multiplication. So this would be 64 times that x plus 2 equals 2. And I'm not going to use the distributive property right there. What I would remind you, to get rid of the natural log has a base of e. So to get rid of the natural log, we're just going to swing that base to the other side. And I'm going to get 64 times x plus 2 equals e squared. Now, you can distribute the 64 here. Remember, e is not a variable, so I'm going to type that into the calculator. What I would maybe recommend, just to save a little time here, I'm just going to go ahead and divide by 64 to avoid having to use the distributive property. So I'd have x plus 2 equals e squared divided by 64. And then all we would have to do to get x alone is subtract 2 from that answer. And I can do that all right on the calculator screen. So e squared, I'm going to hit second natural log button. That should give you e. That's being squared. I'm going to hit equals. I'm going to divide that by 64, and then I'm going to subtract 2, and that's going to give me my answer, which is, to 3 decimal places, negative 1.885. Whoops. Next question, I want to get the e by itself. E is not a variable. It is that number 2.718. So what I'm going to do is isolate that. I'm going to add the 5. Then I'm going to divide by 2. You're going to get e to the 3x. 86 divided by 2 is going to give you 43. Now, to get that exponent down out of the exponent, bring it down on the level with the rest of the question, we're going to swing this. Base of your exponent becomes the base of a log, and then if you guys remember, log base e is the same as the natural log. So really what I have here is 3x equals the natural log of 43, and all I have to do to get my answer is take the natural log of 43 and divide that by 3. So hit your natural log button, 43, make sure you close the parenthesis. And then I'm going to divide that by 3. And my answer, 3 decimal places, 1.254. Now, these last set here in number 5, these you would be expected to do without a calculator. So, and you can use any of the power and root references that you have here. So subtraction is going to get squished together as division. This will be the log base for 32 divided by 2 is 16. If you need to evaluate, what you want to do, just introduce an equal sign, set that equal to x, gives you a spot to get rid of your log by changing this to an exponential. So this would be 16 equals 4 to the x. What you then want to do is either, maybe you know that right off the top of your head, or try to rewrite 16 and 4 so they have the same base. Now in this case, I know 16 is the same thing as 4 squared. If you make the bases match, which I did there, that means the exponents have to be equal to each other. So all of this done, the log base 4 of 16 is equal to 2. Now, I don't have any log property to apply here, so to get rid of the log, I'm going to immediately turn that into an equation equal to x. Swing that over. The 36 stays where it's at. 216, the base of the log, becomes the base of the exponent. You're going to push that x up in the air. Now, both of these numbers, the base they would have in common would be 6. So 36 is 6 squared. 216 is 6 to the third. And so to the x, after that, if I match the bases, then the exponents have to be equal. So what I would do there is do 2 equals 3x. Just solve this little equation, and your answer is going to be 2/3 there. And then finally, I didn't leave myself much room there, but to set that equal to x, I have single log by itself. Swing that 16, 1 over 32 equals 16 to the x. Okay, now 32 and 16 both have 2 in common as a base. Right here, 32 is 2 to the 5th power, 16 is 2 to the 4th power. What I'm going to do here to get rid of the fraction is I'm actually going to move this back up to the top. When you do that, the exponent just becomes negative. When you have a fraction, you got a negative exponent. And then over here, we'd have 2 to the 4x. Okay, once my bases match, which they do there, I just set those exponents equal to each other. So negative 5 equals 4x. I would divide by 4 to get x alone. And I'm going to scooch this up just a little bit. So negative 5 over 4 would be my answer for that last one. This group you have to be able to do without a calculator and show all those steps. And one last problem here. This says the substance has a half-life of 10 hours. The initial amount of the substance is 300 milligrams. So let me remind you what a half-life formula looks like. It's similar to y equals ab to the x. The difference is we have to involve the half-life. So the exponent is x over your half-life. And you know the b value in the case of a half-life problem because it's always going to be half. So this is going to be 0.5 half-life. So we just need to fill in the amount of the substance you start out with. That's going to be the A, the half-life, and that's going to go in for the half-life. So if I'm trying to do the model here, it tells us we have 300 milligrams of the substance. That's going to be your A. Half-life, the B value is always a half. X should be a variable in the model as well as Y. And the half-life here is 10 hours. Now, the next question says, how much of the substance will remain after 18 hours? In that formula, X is time, so this is trying to tell us to plug in 18 for X. So what I would do to answer this question is put in 18 for X, and I'm just going to grab my calculator here. So 300 times 0.5. Now that exponent, you don't have to simplify it, but if you can't see the exponent on your calculator, I would just put parentheses around that. So I want to do 1/2 to the 18 divided by 10 power. So after 18 hours, we'll have about 86.152 milligrams left. And I don't think it says, but I'm just going to go ahead and round to the nearest thousandth like we have been. Okay, last question. After how many hours will there be 60 milligrams? Y is what remains of the substance, so they're actually asking us to plug in 60 for Y. So what that would look like is this. And we don't know how many hours, so X is going to be a variable there. All right, anytime your variable is in the exponent, get rid of this number in front of the 0.5 here. I've got the 300. That's the only thing being taken to the power, so we need to start out by getting rid of the 300. Okay, now in that particular case, if it's a nice number, you can reduce it. You don't have to. You can actually leave that as 60 over 30, 60 over 300, but you can reduce that. That's actually going to be 0.2. Now, the only way to bring that exponent down on the level with the rest of the question is to swing that base and convert this to a logarithm. So it'd be log base 0.5 of 0.2. Then your exponent comes down on the level with the rest of the question, x over 10. Okay, sorry, I didn't leave enough room. I'm going to back up here. I can only do base 10 on the calculator, so I'm going to convert this to base 10 using the change of base. So I'm going to do the log of 0.2, that goes on the top, and then the log of a subscript, which is 0.5, goes on the bottom. That would be equal to x over 10. So I'm going to do this calculation, and then what we'll have to do is multiply both sides by 10 to get that final answer. All right, so I'm just going to grab my calculator, log of 0.2 divided by the log of 0.5. And that'll be that, and then we'll have to multiply that by 10 to get x alone. So this would be, again, I'm just going to go 3 decimal places like we have been, 23.219, and this is going to be in hours. So that's how long it would take for us to have 60 milligrams of that substance left.